Zarzecki from the University of Warsaw. His presentation will be about FoldSAE, a method to steer protein folding through sparse representations.
Hello, everyone, once again. My name is Wojciech Zarzecki, and I would love to tell you about FoldSAE, an interpretable steering for the protein generation. To begin my talk, I would love to start with a brief introduction to the protein design pipeline. To design de novo proteins, we start with the backbone generation with models like RFdiffusion. These models from scratch generate novel protein backbones, the scaffold, the main structure for the entire proteins, and then the remaining parts, the so-called side chains, are filled with another model called protein MPNN. Then generated candidates are filtered with predictive models like AlphaFold, and finally they are tested in a wet lab assays. However, this pipeline is not ideal, even the first stage. RFdiffusion, the generative model for the protein structure, was an essential step for the de novo protein design. However, sometimes working with it resembles rather sampling than the precise engineering. Furthermore, we do not understand how this model works under the hood. Its internal representations are opaque. We do not have where and if has its knowledge about specific properties of proteins. And except for that, we have only broad conditioning input options, so we cannot tell it to generate protein of every desired property we want. So to conquer these challenges, we would love to propose the FoldSAE, the interpretable steering. We want to understand better the generation process, localize specific components within the network which are responsible for the knowledge about these properties, not only to stay on that components level, but move to the neuron level, which neurons are responsible for these properties, and then carry on with providing new steering mechanism via interventions on these neurons to steer the generation toward the generated properties. This method, FoldSAE, consists of 3 stages. The first, localization, wants to find the block of that model which stores the knowledge about desired properties. In an interpretation stage, we want to go even further to that neuron level. And finally, in the intervention stage, we want to use that gathered information to steer the generation process to make it actually not only interpretable, but actionable. So the first stage is the localization. As the name says, it's about finding the block which stores the knowledge about the properties. A block is a stack of repetitive layers within a network. For RFdiffusion, it's quite similar for basic transformer from natural language processing. Such blocks are repeated within the network, and we want to find one which stores the knowledge. So to do that, we make an ablations. By ablation, I mean making a generation with skipping one of the blocks. So basically, output from the previous block is passed as the input to a subsequent block, skipping the ablated block. Such procedure is repeated for every block within the network. Then we analyze generated proteins. If after ablation one of the blocks network is incapable of generating a subset of properties we heard about it, we can conclude that this ablated block is responsible for storing knowledge about that property. To move further in a second stage, we want to go to the neuron level. However, we face a common challenge in deep learning that the activations, which are the product of multiplying inputs to given layer by its waves, are polysemantic. It means one neuron encodes multiple properties at once. So we cannot make any action on that neuron, because if we turn off that neuron, we interfere with multiple properties at once. And to conquer that challenge, we incorporate sparse autoencoders, the SAEs. They are basic autoencoders, which are trained on a reconstruction task of the activations. So we want to transform that activations to some latent space and then back to the original space. And we introduce extra regularization and make that latent space wider to make these activations decompose to the wider region. Therefore, they are more monosemantic, meaning that one neuron encodes only one property at once. And then in the inference, we can carry on with passing it to the further layer. At the intervention stage, after localizing these specific features, the other word for that interpretable neurons, we can amplify the positively correlated ones with target property and suppress negatively correlated ones. And furthermore, we introduce hyperparameter lambda, which allows us to tune the steering strength. Now I will showcase how to approach it technically and showcase some examples how to do steering with FoldSAE. The first stage is building a probing data sets. It's about caching activations of RFdiffusion and SAE and mapping them to the annotations of associated generated proteins via third-party tools or lab assays. Then we can probe for it. It's basically training simple linear model, but with minor difference to the classical learning, some deep learning algorithm or basic machine learning algorithm, that the input is no longer, for example, protein or image, but the internal representation of our network, the activations we want to investigate. And thanks to the fact that it's such a simple network like logistic regression, we can use its coefficients. The coefficients of logistic regressions say how important is each input to that simple network. So the bigger coefficient, the more positively given input to the logistic regression is correlated, and the more negative the other way around, the more negatively correlated. And we can map one-to-one these logistic regression coefficients to the indices of directions of sparse autoencoder activations, so-called features. Therefore, we've got one-to-one map of the feature importance scores of our sparse autoencoder. And we study cases for both categorical properties, such as secondary structure. They are type of conformations of proteins, and there are such classes like helix, strand, and coil. And for such categorical properties, we train one versus rest logistic regression. And for the continuous targets like solvent-accessible surface area, it is how much protein is exposed to the solvent. We discretize these measurements into two bins and then carry on with standard procedure. This slide shows the results of our steering and the effect of the hyperparameter lambda. For the neutral intervention, we've got some helices and strands. However, the more positive lambda, the more helical content we can see, that red curvy lines. However, the more negative, the less helical content. And the same thing applies for the SASA, while the red part indicates the regions of high surface exposure. This slide shows the quantitative steering effect. The experiments run in a bigger scale with various lambda values, and we show that value of lambda is almost directly proportional and monotonical to the steering strength. So if we want to make steering a little bit stronger, we just need to choose a little bit bigger lambda, and if you want to make it less intense, we just need to adjust it the other way. We also run a validation of the generated structures to make sure if they still stay realistic. And to do that, we use a reference proteins generated with, and our proteins generated with the generation. And we embed it with another model, like ESM3, both of the proteins, our generated proteins and the reference proteins. And then we compare the distance between the representations of that models for reference and our proteins. And such metric is called threshold distance, in our case, threshold inception distance. And then we compare distances between them. If the distance is close, it means that generations are close to the reference data. And in our case, that metric for lambda equal to 0 is almost the same as for the moderate lambda range. So it means that steering with moderate lambda does not differ from the interventions, from the generations without interventions, so we maintain biological plausibility. We also extended our setup for the partial diffusion, when we can make generations for already existing protein by noising a little bit protein and locking part we like the most, like the one in circle, and then denoise it back, generating with RFdiffusion, but only the remaining part with FoldSAE steering. In future work, I would love to automate it as an out-of-the-box toolbox for any property with annotated data set, then validate it with wet lab assays, and then carry on with further analysis of activations if other models also can give us more insight to steering RFdiffusion. I would love to thank my collaborators, Paulina Szymczak, Professor Ewa Szczurek, and Dr. Kamil Deja. And thank you, that was all, and I am happy to answer your questions.
Perfect, thank you so much. Are there any questions from the audience? There is one in the back there.
Yep. Thank you so much for the talk. This steering, is it sequential? Like, do you slowly increase the steering and it like learns accordingly? Or can you jump to a certain value in lambda, let's say from 0 to 0.6 directly? And how does the protein fold accordingly? Like, is that a sudden jump, or do you see a small gradual jump even if you change the lambda a lot?
I'm not sure if I got your question right. I will try to answer and ask back if something wasn't targeted really well. So that hyperparameter lambda, can I scroll back? Never mind. That hyperparameter lambda is just a hyperparameter. If you choose the bigger lambda, you've got bigger steering from the beginning of a generation, that you don't need to run first steering with lambda 0.1, then 0.2, and then finally 0.3. You can also pick an arbitrary number. And from the slides which I showed a little bit, and I encourage you to check more examples in a preprint, you can see that the more steering, the stronger steering effect, the more curved protein is. For example, steering toward helices.
Yeah, that answers my question. Thank you.
Okay. Perfect. Then, in the interest of time, I would say we move on. Thank you again for your presentation.
Thank you once again.
And now I would